Okay, so 4 o'clock. Let's go and get started. All right, good afternoon, everybody. How's everyone doing today? Good. Good, good. Week 5, so we're definitely moving. So we're middle of September, so it'll be October before we know it. Okay, so plan for today. We have just one more lecture. I think we should be able to finish up today on constrained optimization. And so we just have one more kind of concept to go over, which are the inequality constraints. Okay, and so we'll go over what those mean, how to deal with those, and a couple of examples for dealing with those. Okay, and then we'll be done with that. And then the next topic that I have planned from here is another kind of large topic called linear programming. Okay, so linear programming is kind of the segue a little bit. It's still, technically we can do a lot of the linear programming problems by hand, but then we'll kind of start to talk about computational algorithms, and it'll kind of lead us into the second half of the class, which is basically all math algorithms. Okay. I think that's about it. This past weekend, I went to a wedding for two people that went to my high school. But they actually, is interesting because in high school they were not, well, it's not that they weren't friends, it's just that they didn't talk to each other because they were in different social groups. But when we reunited, they reunited at our 10-year reunion, which happened in 2019, and when they remet, they fell in love, and so their wedding was last this weekend. So it was interesting because they invited a lot of people from our high school, and you have like kind of two groups of people that normally don't talk to each other, but we're kind of all celebrating the same wedding together. So it was great. It was a fun time. All right, any questions for me before we get started for today? Okay. All right, so let's go and get started. And so the topic for today is inequality constraints. So well, Zoom is lagging again already. Great start to the web thing. I don't know what it is about this time slot. It's the internet is kind of really sucky this time. But anyway, I've had this conversation with a couple people in the class in terms of the types of problems that we've been doing. And in the grand scheme of just optimization in general, all the examples and all the problems I'm having you guys work on the homework are very kind of simple problems. And that trend is going to continue here with inequality constraints too. And it's not that it's not that I'm holding back on purpose. A lot of the methods that we're going over can actually apply to higher dimensional and more complex problems. It's just kind of more busy work to do that. And so as we kind of go through inequality constraints here, yes, we are going to go through methods on how to solve these by hand. But I think what's kind of more important is that you kind of get some intuition and in terms of how the inequality constraints work, what effect that has on the solution, and how can we characterize different things, so that as we get into more complicated algorithms like linear programming, you'll have kind of a good understanding of this. And what we're going to cover today actually leads, it lends itself very well to our next topic, which is linear programming. Okay, so first let's kind of remind ourselves what is an inequality constraint. And so an inequality constraint is a mathematical restriction on our design variables that has some kind of inequalities. Okay. For example, we usually we give our constraints some kind of mathematical form, right? Okay. So we usually give it some function. So in this case, it's g of x1 and x2. Okay. So let's just say, for instance, it's something like x1 plus x2 plus 4 is less than 2. Okay. Less than or equal to 10. And so if we were to draw this out, it would look something like this. So this is kind of the exercise that I had to do in the first homework, right? And so if we were to solve this expression for x2, if x2 is equal to, we actually change this to -4. Okay. -4. x2 is less than or equal to x minus x1 plus 4. Okay. And so if we were to plot that, it would look something like this, right? It'd be just some kind of linear line in the x1, x2 plane. Okay, so the horizontal axis is x1, vertical axis is x2. Okay. And then by the less than or equal to sign, we know that the valid region in this case is going to be below this line. Okay. And so anywhere kind of in this region, kind of below this line, is valid. Okay. Valid or viable, I always forget kind of which terminology that we use. Okay. And so when you look at this, this looks like, this is great, right? And so in terms of freedom of the design variables, like this is a good thing, right? And so if we were to change this to an equality constraint, okay? We have x2 is equal to minus x1 plus 4. Okay. There's a subtle change there, right? We change from inequality to equal sign. If we were to change this to an equal sign, mathematically what that would mean is that that means that our valid solution would have to sit on this line. Okay. That's kind of the purpose of an equality constraint, is that with an equality constraint, we're directly specifying an explicit relationship between the design variables. Okay. An inequality constraint is a lot more lax than that. So the inequality constraint is, basically said that we have this restriction, but as long as you're kind of within this region, then you're good. Whereas an equality constraint is a lot more strict. Okay. So this has a number of consequences. Okay. And so for the equality constraint, this having it be so strict actually works to our advantage, because what this then does is that it simplified our problem. Okay. And so we saw this when we did our direct substitution method, right? And so we know that whenever we have an equality constraint, each equality constraint will reduce the dimensionality of a problem by 1. Okay. And visually, you can see that here as well. And so, we started with a 2D problem with both x1 and x2. But if we were to have an equality constraint, then we know that the solution must sit on that pink line. Okay. And if our solution is on that pink line, we've essentially turned our problem into a one-dimensional problem. Okay. So equality constraints are great for that, because then it kind of reduces the space in which we can look for our solution. Okay. Whereas for inequality constraints, if you look at the region or the dimensionality of the valid region, right? So everything that I've highlighted yellow, yes, there are some restrictions, right? We can't be above that pink line, but strictly speaking, we're still searching in a two-dimensional space. And so, with the inequality constraints, we aren't able to actually simplify our problem, as we did for equality constraints. And so what this gives us is basically a situation where we have these inequality constraints, but but before we actually start the problem, we aren't actually able to do anything with it mathematically. And so they generally inequality constraints mathematically are going to be a lot more difficult to deal with because we can't draw any specific conclusions. Okay. All right, and so that's kind of the challenge before us. And so the challenge before us is we have these inequality constraints. Mathematically, it's very hard for us to kind of use them to simplify our problem right away. But once we get our solution in the end, we need to make sure that the inequality constraint is still satisfied. Okay? And that's going to be a challenge. All right, any questions on this so far? Okay. All right. So let's kind of continue on. Okay. We have a further complication. Not complication, but another way to kind of interpret it. Okay. And so let's say that we have a problem with an inequality constraint, and we solve the problem ignoring that inequality constraint. Okay. In other words, we had our optimization problem, we had our objective function, and we solved it, just like it is, okay? Without any knowledge or any, without accounting for that constraint. Okay. And let's just say that by magic, or not by magic, but just by chance, our optimal design point lands in that valid region. So this can happen a lot, right? And so typically with inequality constraints, you define a certain region of the design space, which has your viable solutions. Okay. And so sometimes just based on your objective function, you just kind of satisfy the snatch. Right? And so for instance, if I go to this figure up here, okay, let's say that we solved our optimization problem and we ended up with the design point right here, okay, in the purple. where the value of x1 and x2 kind of put us right there. So this is great. And so, we solved our problem without having to worry about the constraint, and we kind of just satisfied it automatically. Right? And so it's like that one meme from The Office where Steve Carell's has that blank look on his face. All right, congratulations, you satisfied the constraint, but he didn't really do anything special. Right? So this happens actually quite a lot. And so, but then what does this tell us, right? And so what this tells us is that in this situation, it's almost as if that inequality constraint doesn't exist, or it's like it didn't matter to this problem. And so just that step of laziness where we just kind of ignored it to begin with was kind of the right thing to do in that case. Okay. So that kind of gives us a hint that maybe we have some situations where we don't always have to strictly consider the inequality constraints. Maybe there are some situations where we can just kind of ignore it and just solve the problem just without. Okay, but we can also have some situations like this. And so let's say that we have another optimization problem where the objective function is different in this case. Okay. And so once again, we're going to ignore, for now, we're going to ignore the inequality constraint. Okay. But in this case, let's say that the optimal solution lands outside the valid region. Okay. So we solved the problem as if it were unconstrained, right? And so we used our methods for 2D optimization. We took the partial derivatives, we took the Hessian, okay, without considering the inequality constraint. Okay. And then it wasn't until after we were done that we kind of checked. Okay. So visually, let's say it looks something like this. This figure, unfortunately, is getting quite busy. Go ahead and use this. Just have to select the room. All right. So let's say that we solve our optimization and we end up over here with this big green dot. So I call this P. So P2 in this case violates the inequality constraints. Okay. And so technically P2, even though we call it the unconstrained optimum, we can't actually use it because it violates the constraints. Okay. But it's not useless, okay? And so, just by solving this problem, we know that the optimal solution is in that direction. So we need to go over there. Okay. And so what if we do this? And so what if we take this point and we kind of, find the point that's on the valid region that's closest to that point as possible. Okay. So we move right here. Okay. So this other point, which I'll call P3. Okay. P3, we're going to say sits right on the border of the inequality constraint. Okay, and therefore it's valid. It may not be as optimal as P2, and so its objective value for P3 might be slightly higher, but at the very least it's valid. Okay. And so in this case, what we say is that the inequality constraint is binding. Okay. Remember, we talked about bound points, I think in probably the second week of class. Okay. And so if a design point is sitting right on the boundary of the valid region, we say that that's a bound. Okay. But this also kind of has a very kind of special interpretation. Okay. Because notice how the point P3, it's sitting on that line. Okay. And what did we say earlier, right? When we drew this line, right, this line has the function, has this function right here. X2 is less than or equal to x1 plus 4. Okay. If P3 is sitting on that line, then what we're saying is that P3 is satisfying the constraint in the equality form. Okay. So that's huge for us, okay? Because we already know how to deal with equality constraints, and so we have our Lagrange multiplier method and we have our direct substitution method, okay? And so if we know ahead of time that this inequality constraint is going to be binding, then we can treat it as an equality constraint, and we can solve it in that way. Okay. And so this kind of like thought exercise that we just went through kind of gives us our two scenarios whenever we have an inequality constraint. Okay. On the one hand, if your point is kind of deep within the valid region, and it's not bound by the boundaries, then essentially we can just ignore it. And so we just kind of ignore that constraint because our optimum is just naturally in that area. Okay. The other situation that we may have is that our optimal might be bound by the constraint. And in that case, we treat it as an equality constraint. Okay. And so that's kind of the challenge that we have with inequality constraints. We can either ignore it and be totally fine, or we treat it as an equality constraint in the case that it's binding. Okay. All right. Any questions on this so far? Okay, so all that sounds good, right? And so this at least kind of gives us at least kind of a conceptual path forward in terms of how to deal with this. Okay. The next question that we can ask here is, how do we know, right? How do we know if an inequality constraint can be ignored, or how do we know when it's an equality constraint? Okay. The unfortunate answer is that we don't know. In most cases, it's very hard to look at a problem and say that this constraint is going to be binding or this constraint we can ignore. Okay, and it's going to be even more, I guess, anticlimactic when you look at the solution method, which is basically we're just going to guess and check. So, and so there's formal math theory to this, and so it's called the Kuhn-Tucker conditions. But it's essentially just kind of glorified kind of guess and check. And so we're going to guess, is this one binding? No. Is this one binding? No. Is these two binding? And so that's kind of where we're freaking. Okay, so let's kind of start talking about that. All right, so the Kuhn-Tucker conditions kind of lay out the mathematical conditions for when an inequality constraint is binding or not. And remember, if an inequality constraint is binding, we're going to treat it as an equality constraint. And when an inequality constraint is non-binding, we basically just ignore it. And so we just treat the problem as if it doesn't exist. Okay. So before we can actually talk about the Kuhn-Tucker conditions, we need to kind of remind ourselves of a method that we went over last week, which is the Lagrange multipliers. So and the Lagrange multipliers kind of form the basis of the Kuhn-Tucker conditions. Okay. So we'll just kind of remind ourselves very quickly about what the Lagrange multipliers were and how we're actually going to use them for inequality constraints. Okay. And so if you recall from last week, when we solved a problem with equality constraints using Lagrange multipliers, we formed this kind of augmented objective function. Okay. Because what we were saying was that, instead of treating the equality constraints kind of separately, we can just kind of incorporate them directly into our objective function. And that's one way to do it. Okay. And so what we said was that our augmented objective function was f of x vector. Remember, f here, that's our original objective function. Plus, we had a summation of all of our Lagrange multiplier terms. Okay. Remember our GIs here, these GIs are our constraints in standard form. But more importantly, these lambdas are our Lagrange multipliers. And so to solve a problem with Lagrange multipliers, we basically set this up and we solve the equation for both, you know, the values for x as well as the values for lambda. Okay. And so we're essentially basically solving a bigger problem. So the problem for both the values of x and the values of lambda. Okay. All right, so those are kind of the problems and the examples that we did last Thursday. But if you recall from last Thursday, you know, we didn't really talk a lot about the values for the Lagrange multipliers. And so I told you that, you know, this is the method, we can solve for them, but we don't really use them just yet. Well, now's the time that we're actually going to use them. Because the values or whatever you get for the Lagrange multipliers actually has some significance. And to kind of talk about that, you know, we can talk about the you know, or first we kind of note the fact that, you know, each constraint is associated with one Lagrange multiplier. Okay. And so kind of based on kind of the mathematical form there is that, you know, if we have just one constraint, we have just one Lagrange multiplier. But if we have two or three constraints, you know, we'll have Lagrange multiplier 1, 2, and 3, and each one is going to be assigned to each constraint, basically, right? So there's a one-to-one kind of matching between a Lagrange multiplier and its constraint. Okay. And so that means, or that kind of implies that whatever value that we get for the Lagrange multiplier tells us a little information of, you know, what effect that constraint has on our solution. Okay. In particular, you know, the one that's going to be kind of relevant for us for the inequality constraints, if we get a value for 0 for the Lagrange multiplier, okay, what that tells us is that that constraint had absolutely 0 effect on our solution. In other words, we could have just ignored it from the beginning. So for example, we've been talking about the theory this whole time. So let me give you some numbers and some values. Okay. And so let's say that we had kind of a very simple optimization, 2D optimization. Let's say that we had an objective function x1, x2 is equal to x1 squared minus 3x2 plus 14 x1, x2. Just made it up right now. Okay. And so let's say that we had two inequality constraints for this problem. We'll have G1, x1, x2, 2, maybe x2 plus 15x1 plus 14 is less than or equal to 0. Okay. And G2, x1, x2 is equal to 1 over x2 minus square root of x1 plus 4 is less than or equal to 0. I'm just making stuff up right now. You kind of put that in red so that if you go back and kind of check your work, it may not be exactly what I say, but just kind of illustrating this fact. All right. And so in this problem, we have two design variables, one objective function and two constraints. Okay? Both constraints are inequality type, and so even though we have only two design variables, we can have two inequality constraints. Okay. Let's say that we solve this problem, and we found out that the Lagrange multipliers for these two. Okay, so each of these constraints are going to have a Lagrange multiplier associated with it. Okay. And so let's say that we found lambda1 is equal to 0. And lambda2 is equal to, I don't know. What's your favorite? 6. 6 is my favorite. Okay. What this means is that, because lambda1 here is equal to 0, that means this constraint here has no effect on the solution. Okay? And so since this has no effect on the solution, we can effectively just ignore it, or we can say that it just doesn't exist. So if we were to kind of solve this problem again, then we would just solve it with just the second constraint, because that's the only one that's actually having an effect. Okay. Any questions on this? All right, and so this kind of gives us kind of a framework for our Kuhn-Tucker conditions. And so we're basically going to use the Lagrange multipliers as our framework for determining which constraints we can ignore and which ones we can incorporate. Okay. Okay, so let me go ahead and kind of write them out kind of explicitly. So it's a little bit long, it's a little bit stuffy, but I'll go ahead and summarize it afterwards. Okay. All right, so the Kuhn-Tucker conditions state this. So we have a partial f. One xi plus summation I to the 1 m I sorry, so this should be summation j is equal to 1 to j partial g j xi equals 0. Okay. Right, and so that's a series of equations, and so xi there indicates that we do this for each design variable. Have lambda j gj is equal to 0, so that's the kind of the dot product between the lambda vector and the constraint vector. And we have gj is less than or equal to 0. And then lambda j. So with these three statements kind of combined, what they tell you is that you either have two things. Okay. So what this tells you is that if lambda is equal to 0, or a corresponding constraint, if lambda is equal to 0 for a corresponding constraint, that means we can ignore it, right? So that constraint is non-binding. But if lambda is not equal to 0, okay, in this case we're assuming that the lambdas are greater than 0, then that constraint is binding, and we treat it as an equality constraint. All right, so we're never going to use kind of the full mathematical form for the Kuhn-Tucker conditions, but we are going to kind of use this kind of theory. Okay. Okay. Any questions on this before we jump into an example? Okay. All right. So let's go ahead and do an example. All right. So let's maximize the following function. Okay. It's going to be a two-dimensional optimization, and so we're going to optimize f of x and y. So x and y are our design variables in this case, and so we're just going to optimize the product of the two, x times y. And we're going to have two inequality constraints. So we're going to have x plus y must be less than or equal to 50. 2x plus y, we're going to say has to be less than or equal to 60. Okay. Right. And so just like any optimization problem, we want to find the values for x and y that maximize our objective function. Okay. So that's the problem that we're dealing with, right? So we have a fairly simple objective function, but we have inequality constraints. Okay, and so we need to make sure deal with that. Okay. And so kind of the goal at this point now is to find out, which of those constraints are going to be binding and which ones are going to be, non-binding or weakening. Okay. But we don't really know. It's really hard to tell just looking at this, which ones are going to be binding or not. And so we're going to take kind of a guess and check approach. So we're going to guess, maybe this one's binding, maybe neither of them are binding. We're going to solve for the optimal solution. We're going to check to see if our solution is still valid, and if not, then we kind of go on to the next thing. So this is basically what we're going to do. We're going to guess. Constraint is binding. Two. Once we have a guess for which constraints are binding, we can then solve the problem as a problem with equality constraints. Optimize the problem, as we typically do. Okay. Then number three, we're going to check. We're going to check to make sure that our optimal solution still satisfies all the constraints. Right, so that's going to be our approach. Okay, so I'm going to track each guess, and so I'm going to call them try one, try two, try three. All right, try one. And so, usually this is not going to be the case, but it's always good to try just in case. And so let's try to see, maybe neither constraint is binding. So we just solve the completely unconstrained problem. And so if we just solve this completely unconstrained, we have f of xy is equal to xy. Okay. It's a 2D problem, so let's take our partial derivatives with partial f, partial x is equal to y, is equal to 0, the partial f, partial y, x, that's equal to 0. Okay. And so our optimal point in this case is x is equal to 0 and y is equal to 0. So it's a solution like this we often call it a trivial solution. So you kind of could have figured this out without really doing much work. Okay. Let's check to see. First, let's check to see if this satisfies our constraints. But then we also need to check and see if this is actually a maximum or not, or maybe it could be a saddle point. Okay. Okay. So our two constraints. Our first one is x plus y has to be less than or equal to 50. Okay. And so this is our constraint number one. Let's plug in for x and y. So we have x is equal to 0, plus y is equal to 0. And so we have 0 plus 0 is equal to 0. And so that's less than or equal to 50. So that's good. That checks out. Okay. Our other constraint here is 2x plus y has to be less than or equal to 60. Let's go ahead and plug in for this. So we plug in for x is 0, y is 0. We have 2 times 0 plus 0, which is equal to 0. And so that's also less than or equal to 60. And so that's good, right? And so with this solution right here, we have something that satisfies all the constraints, which is good. Okay. But we need to check to see if this is actually a maximum or not. Remember, the way that we do that in multidimensional problems is we compute the Hessian. So let's compute our second partial derivative. So we have partial squared f, partial x squared is equal to 0, partial squared f, y squared is equal to 0. And then we have the cross term, partial squared f, partial x, partial y is equal to 1. Okay. And so if we form our Hessian matrix from this, yes, 0, 1, 1. Okay. And so remember, in order for this to be a maximum, this matrix here needs to be negative definite. Okay. And so to be negative definite, the first principal submatrix has to have a negative determinant, and then each one after that has to be positive. Okay. So let's check the principal submatrices. Okay. We have A1. Remember, A1 is just the top left entry, so A1 is equal to 0. Okay. And then for A2, we're going to take the determinant of this square matrix here. So this is 0 and 0 minus 1 times 1 is equal to minus 1. Okay. All right, and so since our first principal submatrix here is 0, we can just kind of conclude right away that this point here is not a maximum, but it's a saddle point because we have a semi-definite matrix. Okay. And so even though we were able to find an optimal solution in this case, and that optimal solution just automatically satisfied both of the constraints, this optimal solution is not a maximum. So it's a saddle point. And so we kind of have to continue on this. Okay. And so what this is telling us is that the true maximum of this function is going to be bound by one or at least one of the constraints. Okay. All right, any questions on this so far? Okay. All right, so let's go ahead and continue. Let's go ahead with try 2. Okay. So try 1 ended in failure. So even though we found a solution that satisfied the constraints, it was not a true maximum. And so we know that our optimal solution here is going to be bound by those by those constraints. Okay. And so for try 2, we're going to assume the constraint x plus y is less than or equal to 50 is binding. First constraint is binding, but the second constraint we're going to assume is non-binding. And so we're going to form our Lagrange function in this case with that only that first constraint. Okay, so we're going to have 3 variables that we're going to deal with here. So we have x, y, and lambda 1. Okay. So we're going to go ahead and form our augmented objective function. And so it's going to be x times y, right? Remember, x times y, that's our original objective function, plus lambda 1 multiplied by. Then we're going to put our constraint in standard form. So in standard form, our constraint is x plus y minus 50. Okay. So now what we're going to do is we're going to solve this constraint problem as if that first constraint were an equality constraint. Okay, but we're ignoring the second constraint because we're assuming that that one is non-binding. Okay, so let's go ahead and solve this. We have 3 variables here, so we're going to take 3 partial derivatives. So we have partial L partial x, partial L partial y, partial L partial lambda 1. All right, so partial L partial x, we compute this, we get y plus lambda 1 is equal to 0. Partial L partial y is going to give us x plus lambda 1, so we get 0. And then for the last equation, we get x plus y minus 50 is equal to 0. Okay. So we have 3 equations here and 3 unknowns. So luckily for us, this system here is pretty easy to solve. And so I'm going to take these, the first 2 equations, and we can solve for both of them for lambda 1. Okay. Or you can kind of do what I normally do, and then you can just subtract the 2 equations. But if you solve for lambda 1, we get y is equal to minus lambda 1. X is also equal to minus lambda 1. So this tells us that x is equal to y. Okay. All right, so let's go ahead and plug that in here. Right, so if x is equal to y, we could just either use x or y. We get x plus x minus 50 is equal to 0. Therefore, 2x is equal to 50. X is equal to 20. Okay. And if x is equal to 25, we know that x and y have to have the same value. So if x is equal to 25, then y must also equal to 25 as well. So that right there is our optimal solution. Okay. Let's check to make sure that this satisfies the other constraint that we ignored. Our other constraint stated that 2x plus y has to be less than or equal to 60. Okay. Let's go ahead and plug in for the values for x and y. Okay. We have 2 times x, so we have 2 times 25 plus y, which is 25. Okay. We add these together, we get 2 times 25 is 50, 50 plus 25 is 75. Is 75 less than or equal to 60? No, it's not. Okay. And so this solution, even though it's optimal, violates the second constraint. And so this is an invalid point. And so we're going to have to go through a next try. Next one's the final one. I'll kind of spoil it a little bit and try for another optimal solution. All right. Any questions on this try right here? Yeah.
How come if you plug in, so x is equal to 25, plug it in into the second equation, x plus lambda 1, you get negative 25. That's non-zero.
For the lambda? Yeah. So lambda 1 we assumed is non-zero. Lambda 1 has a non-zero value because we assume that one is binding. And so that's kind of what we formed here mathematically by making this equation. We assume that lambda 2 is 0.
Okay.
Yeah. And so in the next try, we're going to assume that lambda 1 is 0, but lambda 2 is non-zero. Yeah. Good question. With all the lambdas kind of going around, it's kind of hard to keep track of everything. Okay, so let's go to try 3. Okay, so let's assume that the second constraint, 2x plus y less than or equal to 60, we'll assume this one is binding. Whereas the first constraint we're going to assume is non-binding. All right, so let's go ahead and go through the same procedure. We're going to form our Lagrange function. Just for kind of clarity here, I'm going to call it lambda 2, okay, for the second constraint. So xy plus lambda 2, 2x plus y minus 60. Okay. So this is now our Lagrange function. So let's go ahead and take our derivatives. So we have partial L, partial x. Partial L, y, L, partial 2. Okay, so we solve for this, we get y plus 2 lambda 2 equal to 0. X plus lambda 2 equal to 0 for the second equation. For the last equation, we have 2x plus y, 60. All right, so a slightly different system, but still with a fairly simple solution. Okay, and so just like before, I'm going to take the first two equations and solve them for lambda 2. Okay, and so we get lambda 2 is equal to minus y over 2. And from this one, we get lambda 2 is equal to minus x. Okay, and so we set these equal to each other. And what we get is minus y over 2 is equal to minus x. Therefore, 2x is equal to 1. All right, so whatever value we get for x, y is going to be 2 times that. Okay. All right, so let's go ahead and plug it into this equation here. Okay. And so we plug in for 2x. We see that 2x is equal to y. And so we get y plus y minus 60 is equal to 0. Okay. This gives us 2y is equal to 60. And therefore, y is equal to 30. Okay. If y is equal to 30, that means x is equal to 1/2 of that. So that tells us that x is equal to 15. Okay. And so we have a new optimal point here where we use the second constraint as our binding constraint. Okay. So now that we have this solution, so this solution here at x is equal to 15 and y is equal to 30, this assumed that the second constraint was binding and the first constraint was non-binding. So let's check to make sure that this still satisfies our first constraint. Our first constraint was x plus y has to be less than or equal to 50. Okay. So let's plug in the values for x and y here. So x is equal to 15 plus y is equal to 30. So 15 plus 30 is equal to 45. And we see that 45 is indeed less than 50. Okay. And so our first constraint is satisfied. And so that's good. And so, our last try here kind of yielded our solution. So this solution here, x is equal to 15 and y is equal to 30, this right here is the optimal solution for this problem. And of course, you can go and check, because we did a Lagrange multiplier problem, we have to do that augmented Hessian, what we talked about last week, okay? But if you go through that process, you'll see that this solution here is indeed a maximum of that function. All right. Any questions on this? Okay. All right, so I do have one more example in the notes. We only have 5 more minutes left in class, and so we're not going to be able to finish it. But I at least kind of want to start it for you a little bit, just so that you can kind of finish reading it in the notes. But with this, you should be able to finish the last problem on the homework, problem 4, because problem 4 is, you basically go through the same process. Okay. Okay, so let me talk you through the last example, just kind of in concept. Then you can kind of read the rest of the details of it in the. All right, so this last example that I have here is a much more practical example. Okay, and this actually has to do with kind of business planning, actually. So this is kind of a business planning kind of example. Okay. Okay, so let's say that you work for a company that manufactures refrigerators. Okay. And then as kind of the director of resource planning at this company, you're trying to decide how many refrigerators should you plan to manufacture each month, okay, for the next 3 months. So you're given the following information, and so for any given month, the total cost to produce refrigerators is given by the following formula. X squared plus 1000, okay? Or X here. This X represents the number of refrigerators that you're going to manufacture that month. So this is a pretty standard formula, and so generally speaking, when you're talking about the cost to manufacture something, there's usually a fixed cost for each month, and so that 1000 may represent maybe maintenance on the machines, maintenance on the tools that are used to manufacture these refrigerators. Okay? So that's something that's fixed each month, and then you have scaling costs, which scale up depending on how much output that you give. Okay. And so X here represents the number of refrigerators. And so the number of fridges that you produce, or the more refrigerators that you produce, the more the cost is going to be. Okay. And so that's usually in the cost of materials, labor, fixings and things like that. Okay. And so or the company knows that there's going to be demand of at least 50 refrigerators each month. Okay. And the company must meet those demands because it's contractually obligated to meet those. And so at the very least, each month you have to produce at least 50 refrigerators. Okay. With that said, the company is able to overproduce. And so, if you produce more than 50 refrigerators, you can put anything in excess of that in storage. Okay? The problem is, storing those excess refrigerators is going to cost money. Okay. All right. And so with this said, what you're going to do in the problem, and the problem itself kind of outlines this better, is that this company wants to minimize its cost, just like any company would like to do. Okay. So based on that formula there, and based on the fee that it costs to kind of store the extra refrigerators, and kind of based on the demand, you want to solve the optimization problem to determine how many refrigerators should it produce each month. Okay. With the constraint being that at least 50 refrigerators have to be produced each. Okay. And so this is actually a 3D optimization problem. And so one of the very, very few that I actually go into the third dimension, because it's we're planning for kind of 3 months in advance. Okay, and so I think it's a useful problem to look at, it's just, we're gonna go through the same process. Dealing with inequality constraints unfortunately is kind of a tedious thing. But if you want to see kind of the process again, I would encourage you to look at that example, especially if you're having trouble with the homework. Okay. All right, any final questions on this before we wrap it up for today? Okay, all right, so that's all we got time for. And so this kind of concludes our section on the classical methods. And so starting on Thursday, we're going to start talking about linear programming. Okay. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your day, and I will see you guys on Thursday.
Yeah.
Yep. Okay. Sure.
So. Yeah, no, you, I don't know.
Oh, yeah. So there's I missed it here. Someone pointed out.
I'm getting similar values to me. And I was wondering, here's my word.
Yeah.
I projected, it's getting the same values.
So I think the issue is here. So 200 gigapascals is 200 times 10 to the 9.
Oh, okay.
So you're right. So it would be 2 times 10 to the 11s, but it would be 200 times 10 to the.
Oh.
I think if you do that, then the number should.
Okay, yeah, thank you.
You guys. Thank you. Yeah, more. Sorry. I saw your question, but someone else has. Y is greater than 3. Oh, I think that's a typo. So I changed that problem so that it doesn't, it should satisfy that. I think it should say y is greater than 2. Yeah, so I think that's a typo for that. So it should say y is greater than 2. So yeah, let me go correct that. It was 3 at first, but then it started becoming a little bit complicated at the end. And so yeah, I changed it to 2 just to make it move. Okay, I'll go correct that after the class or after my next class. Yeah. Yeah. There's an extra 0 there. Yeah, someone pointed that out yesterday and I forgot to put it.
I'm trying to solve this one. So 5 is on this constraint.
Yep. Yep.
So I have this constraint, solve for. Look it back to the objective function. Take a. Yeah, I take the. But I'm gonna get it.
I think I rounded down. So what I did was yeah, it's probably like 40 point something, and I just kind of rounded down from there because it has to be kind of a whole. But I'll double check my work for that one. Sure, I might have made it kind of small with that one, but I remember that's kind of what I did. It's like 40.7 or something like that, and then I rounded down to just 40, and then I used the constraint to solve for y. But I'll double check that just to make sure.
All right. Thanks.